Now that we're equipped with the full definition for a qubit, let's take a look at a few adjacent but important concepts. In the previous video, we arrived at this definition for a qubit, which consists of a column vector with components alpha 0 and alpha 1, where these entries are complex numbers that when we take their modulus squared, they represent the probability of measuring either state 0 or state 1, and therefore must also meet the condition that when we add them together, they must be equal to 1 to respect the fact that these are probabilities. Now we arrived at this expression by way of example using the spin of an electron, for which we actually derived this expression that depends on the parameters theta and phi, which correspond to the angles at which an electron is pointing at with respect to the positive z direction and the positive x direction respectively. We also mentioned that this angle of phi is what is known as the relative phase, since it represents a phase difference between state 1 and state 0, and this value of gamma is what is known as the global phase, which, since it multiplies both the probability amplitudes for 0 and 1, has no consequence in the values that we observe for the probabilities of measuring these two states. Now, even though we arrive at this expression using the spin of an electron as an example, we also mentioned that it's fairly common to use this expression for a general qubit as a visual representation in what is known as the Bloch sphere. So in the Bloch sphere, our qubit is represented by a vector of unit length pointing in a direction determined by the angles theta and phi. So with all this in mind, let's now introduce a few important concepts related to this definition of a qubit. And the first one is that of a Hilbert space. So we can think of a Hilbert space as the family of all the possible vectors that meet this definition. Technically speaking, this definition is only a subset of what is known as a finite dimensional complex Hilbert space over the complex numbers that is equipped with an inner product that induces a complete norm. But these details are not that important at this point. All we need to know is that when we talk about the Hilbert space of our qubit, it's basically the family of all possible values it can take. And we usually denote this as our qubit Q belonging to this Hilbert space of dimension 2, because we're talking about vectors with two complex entries. The next important concept is that of what is sometimes called the covector or the dual vector of our state vector Q, which is represented by the bra of our state vector, which was a concept we introduced when we discussed the vector representation of classical bits. But as a reminder, what we said there is that the bra version of our ket is the row vector representation, but in the case of our qubit, we also need to take the complex conjugate of its components. So with this, we can then define the inner product between two state vectors. So let's call them x and y, both belonging to the same Hilbert space, as the product of the bra of one of the vectors with the ket of the other vector. So that will give us, for example, if x has components x0, x1, since we're taking the bra, that will be the complex conjugate of those entries times the column representation of y with components y0 and y1. And if we multiply these two, what we get is x0, y0 plus x1, y1. Now, an important thing to mention here is that unlike what we had for classical bits where our entries were only either 0 or 1, since here we're taking the complex conjugate, performing the inner product between x and y is not the same as performing the inner product of y and x, because this one will give us x0, y0 complex conjugate plus x1 times y1 complex conjugate. And these two are not necessarily the same. Now, one thing that the inner product allows us to do is find the length of a vector. So if we take our qubit Q and perform the inner product with itself, well, what we get is assuming it has components alpha 0, alpha 1, we have alpha 0 complex conjugate times alpha 0 plus alpha 1 complex conjugate times alpha 1, which is equal to alpha 0 squared plus alpha 1 squared, which, if this is a proper representation for a qubit, we know that it must meet the condition that this should be equal to 1. We can also define what is known as the outer product, which is basically taking the product between a ket, let's say x, with the bra of another vector, let's say y. So if we do that, what we have now is x0, x1 times the row vector y0 complex conjugate, y1 complex conjugate, and what we're going to get from this is actually a matrix. Since we need to multiply x0 with y0 complex conjugate, then x0 with y1 complex conjugate, then x1 with y0, and then x1 with y1. And later on, we'll discuss some situations in which performing the outer product is of value. And the last thing I want to discuss is the concept of an orthonormal basis. So an orthonormal basis is a set of vectors that we can use to represent any other vector in our Hilbert space as a linear combination of this basis. So for example, state 0 and state 1 form a basis, and we typically call this the computational basis or the bit basis. Another popular basis is the one composed by state plus and state minus. And the reason these are orthonormal is because if we take the inner product between state plus and state minus, this is equal to 0, meaning that they're orthogonal to each other. And they're both normalized states. So if we take the inner product of state plus with itself, it's equal to 1, and state minus with itself is also equal to 1. And this is typically known as the Hadamard basis or the sign basis. But in general, a basis is composed by any normalized vector, let's call it u, and another vector, let's call it u perp, that meets the condition that both of them are properly normalized and their inner product is equal to 0. So now let's go to Qiskit and take a look at a few functions related to these concepts. So here we're only going to import the state vector class, and let's define two state vectors. Let's call one QA, and let's use this from label function and define it as state plus, and then QB and define that one as state 0. So we can perform the inner product between these two state vectors by taking one of the two and using this inner function and passing the other. And what this is going to perform is the inner product between the bra of the original vector and the ket of the one we're passing. And if we do that, it should give us a number that corresponds to that inner product. Now, of course, we can also perform the inner product of a vector with itself that we know that if it's properly normalized, it should be equal to 1. Now, the thing is that Qiskit does allow us to define state vectors that are not necessarily normalized. So we can take, for example, a vector with entries of 1/2 and 1/3. And we know if we take the norm square of these two values, they're not going to add up to 1. And we can actually display that vector. And the state vector object has actually a function called isValid that allows us to see if the vector is normalized or not. And in this case, since it's not, we're going to get a value of false. If we do it for, let's say, QA again, we should see that that's true. But we can normalize our vector by defining its length. The way we do that is, let's call this QN length. And we take the inner product of that vector with itself. And that should give us the length of that vector squared. So if we now take the square root, and for that, let's actually import the square root function. So from NumPy, import square root. So if we do that, square root of the inner product of that vector, and then take that original vector and divide it by that length, it should give us a vector that is properly normalized. Let's actually store this again in the same variable, qn. And now if we do qn.isValid, it should be equal to true. And here we have it. So that's it for this video. Hope you found this helpful, and I'll see you in the next one.